Start recording. So a standard solution is a solution of accurately known concentrations. So it has to be accurate. We did talk about this the other day, but I wanted you to have it officially printed out somewhere so you'd think it was important, because is it important? Yes. Okay. And a primary standard, again, we talked about this the other day, but we just sort of scribbled it on the side of the page. So I wanted to make sure that you had it on a handout, which if you weren't here at the beginning of class, you're going to come and get one of these. So a primary standard is something that is pure and stable, and it will not absorb water or CO2. And it has to also be a solid. Is good? Okay. If you have these three things where it does not absorb water or CO2, where it is a solid, where it is pure and stable, this means that you can measure the mass very accurately. Yes? Well, a substance that can be used to make a primary standard solution. If you would like me to put more words in there to make it more awkwardly, but that, I mean, that's really what it means. Do you know what I mean? Yeah, we can throw that in there. So therefore, a solution of this substance will have an accurate concentration. Okay, and a primary standard is a substance which can be used to make a very accurate solution concentration. Do you see why I didn't put it in there? It becomes really wordy. So don't feel any need to like put that in there. Okay, it's really just semantics. Okay, I'm going to erase that because it gets very confusing. There we go. So that's a primary standard. Now you will see standardized solutions. You will say, oh, I have an NaOH standard solution. NaOH is terrible. It absorbs carbon dioxide and water from the atmosphere like nobody's business. So a standardized solution, if we have a substance which does not have the characteristics of a primary standard, so a substance which does not have the characteristics of a primary standard, in other words, maybe it is like HCl, is a gas. It is actually bubbled into water to make concentrated HCl, and then you can dilute it from there. Okay. If you have NaOH, it absorbs water, and so it won't be very pure. All right. So, but if you have something that is not a primary standard, it can be standardized, which means an accurate concentration can be found. And you do that by titrating it against a primary standard. Is good? Okay. So here, for example, we have NaOH, and this is like directly lifted right out of Hebden. So if you want to go to the source, this is page 156. And I think I've put it as reading down on the bottom. Sodium hydroxide cannot be used as a primary standard because generally it is only about 95 to 98% pure. Is that very pure? No. All right. Also, it absorbs water. It's missing an and. Look, Hebden has typos too. And carbon dioxide. Absorbs water and carbon dioxide. Sorry, I put the and in the wrong place. Water and carbon dioxide. There we go, that's better. Rapidly upon exposure to the atmosphere. However, you can make a solution which is approximately 0.1 molar by measuring out the mass, because it's not going to be that far off. I mean, it is 95% to 98% pure. It'll be close. And then you can use a primary standard. One of the primary standards, I cannot imagine that you'll be responsible for knowing this name, but here we are. It is, like, you won't on my test for sure. Where are they? There we go. Potassium hydrogen phthalate with that lovely PHTH, like phenolphthalein. Okay, so we have potassium hydrogen phthalate is a primary standard. You will make that by measuring out a known mass of potassium hydrogen phthalate. What kind of container would you use to make this solution? This is going to be on the AP exam. I almost guarantee there's going to be some sort of question that needs you to know how to make a solution. It might only show up in the multiple choice. You might get lucky and be able to just pick one from a list, but it might show up in the written response. We want it to be very precise and very accurate, right? Because we're making a primary standard. And you've actually made solutions at least 3 times now using this piece of equipment. Like literally physically in the lab, you have used this piece of equipment at least 3 times between grade 11 and now. A volumetric flask, thank you. Flask. Could you draw a picture of what a volumetric flask looks like-ish? I mean, I can only ish draw one, but see if you can draw a little volumetric flask.
Oh my God. Oh, shit.
Okay, and it has a calibration line, so it'll make either 100 milliliters or 250 milliliters or 500 milliliters. There are 25 milliliter volumetric flasks. Okay, it's sort of the gold standard for making a solution because it's got that narrow neck. So a small change in volume means a bigger change in height. So you're not going to be like, oh, I could add 3 drops and not have it move up and down very much. Or I could add 3 drops and have that change it quite significantly. Yes?
When you use an Erlenmeyer?
You use an Erlenmeyer flask. It is very inaccurate and imprecise. You use it for containing liquids. Okay, so you might mix things. It's really good for mixing things because it has that narrow shape. It's not like if you have a beaker and you're swirling it like this, unless it's right down at the bottom, you know, things could splash out. Not as big a deal if you have a magnetic stirrer. There are little magnetic stir bars that will stir for you, and then a beaker is not a bad choice. But when we're doing a titration, it's perfect because we can stir, we can swirl without having it be a big deal. So it's more for containing and mixing than it is for like making a precise solution. Okay. All right. So that's all you need to know about standards. There are some questions on page 165, number 121 to 123, and you can read pages, oops, that should say 164 to 165. Typo there. I'm going to let you do that on your own. And we are right now going to do a couple of actual titration questions. Again, I lifted this right out of Hebden. Titrations are often performed to find the percent purity of a solid acid or base. There are many, many different ways to do this calculation, but most students find this procedure the simple to follow. Calculate the concentration of the acid or base using the concentrations, volumes, and base acid mole ratio given. Well, what is it saying? It's saying do the stoichiometry calculations that you would do for any titration calculation. And what are those stoichiometric calculations? We should be going from our known substance, and probably we have milliliters and molarity. That's what's usually given to us. And then the first two steps are always the same. The third step can vary. And everybody should be able to fill in what comes after arrow 1 and after arrow 2. What's at the end of arrow 1? Moles of known. You guys are gonna kill me. It's gonna kill me if you guys can't figure out number 2. So I want you to really think and ask around if you don't know it. You need to convert to everybody. Moles of the unknown. Yes, thank you. All right, we've already done titrations in grade 11. We did them in the solubility unit. Yes, we are doing them again now. And guess what? We're going to do them again in redox. And I think this is a really straightforward calculation. And shockingly, people manage to do it wrong on a regular basis, which just, like, I don't get why, because we're always just converting to moles of known and then moles of unknown. I think maybe people get confused about what the reaction is or how to find the final thing, maybe. That might be what's going on. I just don't know. Anyway, you're going to find either grams or molarity or whatever it's asked for. Now, Hebden wants us to use the mass of the impure solid to calculate the expected concentration. This would be the concentration if the acid were pure, if the substance were pure. And the actual concentration would be found from the stoichiometric calculation, from the titration calculation. And that's how one way you can do percentage purity. However, there's another way you can do percentage purity as well. The percent purity could be the mass of the pure over the mass of the impure. Does that make sense? Okay. And then, of course, times 100%. And it doesn't matter which one of these calculations you use. There are other ways to do it as well. I would like you to see if you can use that and your general knowledge to do this example. Yes? Which one is bigger? Why? So what I've got is I've got a sample here of my stuff. Say it's 10 grams. And let's say this is let's just say this is NaOH. Yeah, because we know that one becomes impure. All right? Here, this part of it is, we said it absorbs water and carbon dioxide. So the impure is 10 grams and the NaOH is however much will react with the thing it's being titrated with. Okay, so the pure will be smaller and the impure will be bigger because it contains both the pure plus the impurities. Yeah? So if we have mass of impure, it's equal to the mass of the pure plus the mass of the impurities, whether those be H2O or CO2, etc. It could be anything in there. You know, if you just didn't have a very good sample and somebody threw something else in there, you'd be like, oh, okay, you know, yeah. Okay, so give that question a try. See what you can do. I'll try it both ways. What did you guys get? I got 92.18, but you probably just rounded before I did. Or I got the molar mass wrong. I kind of like Hebden's method. It makes it easier because you're taking, some people get messed up when you take 25 mils of a 250 milliliter sample and they forget to multiply by 10 when they're finding the mass. But we can do that also. Do you want to do it the other way? Would we like to see it the other way? Okay, we're going to do it the other way as well, but we'll let you hang with this for a minute. If you would like a printout of this too, and not just have to scribble it down, I can just print it for you. Anyone want me to print it? Okay, at least 5 of you, which means I'll make a class set. Ha ha ha! It's about how many, I guess. Sorry. Hi. Yes, of course. Help yourself. Okay. Should I try the other way now? Yeah. How about you guys also try it the other way? See if you can do it with mass over mass. Or if you did it with mass over mass, see if you can do it with concentration over concentration. Whichever way you did it before, do it different now. Do it the other way. So the two formulas, we have actual over expected concentration, or we have mass pure over mass impure. I'll write those down again. In fact, I can just take a picture of it. And pop down here and throw it there. Oh, that didn't work. That's okay. So if you did method 1 before, do method 2. If you did method 2 before, do method 1. Is good? Help yourself to extra paper if you need extra paper. .4786. Mm. That can't be right. That is not, I'm doing something very wrong. Oh, there we go. Whew. Okay. Good. That's much better. Okay. Are you guys happy just seeing it, or do you want me to walk you through it? You're happy just seeing it? Or did you want me to walk you through it? You also did it, so you're good. Okay, very cool. This would be, if I were marking this, I would be like, why is the percent purity hiding up at the top? It's in no logical order. I would normally put that down at the bottom, but I wanted it all to fit on one screen for you, yes? So I would be like, okay, here we go. Yeah? If I had actually written it that way and I expected somebody to mark it, I would show that I had gone from here up to here, but I wouldn't normally write it that way because AP gives you tons of space in which to write. So you should not, I don't think, run out of room. Okay? There we go. Somebody wrote an amazing essay about Niels Bohr, and the first word of every line in the essay about Niels Bohr and quantum theory is a rickroll. It's pretty awesome. If you can find it, it's a good one.
Is it like a good essay?
It's not bad. Like, it doesn't sound, necessarily contrived. I mean, I didn't read the essay really carefully because I wasn't that interested in its content, but are we good? Okay. If you're good with that one, why don't you try molar mass determination on the next page? Why is it always in milliliters? Because what does your burette read? Milliliters? Yes,
So, do I have? So I wrote this right.
that should be fine. Yeah.
Do I have to write the reaction?
I don't know.
Okay.
Yeah.
Cause like I'm telling you that this is
Yeah,
true,
no, it's probably fine.
so I don't have to write the reaction.
I'm
I,
not
like,
saying that. I'm
okay.
saying for me that would be okay. I don't know about AP.
Alright.
Okay? I feel like I've done something wrong. This seems way too big. Oh, maybe I didn't. Oh, yeah. No. Yes. No, yes. Did we get 158.1 grams per mole? Good. So tomorrow we're going to do oxides. I almost had the oxide thing finished, and then I found this really good video, and I'm like, oh, I want to include some of that stuff on the oxides, so I didn't finish oxides today. So there are questions in your workbook on page 110. Some of them are, oh yeah, no, it's good. Yeah, it'll be okay. Okay, so you guys can start working on that. Does everyone have access to Hebden? Either they've got the book or they've got the online version? Okay, good. Anyone want to have the quiz on Thursday as opposed to Friday? We're having a quiz. Well, you guys said you said you wanted a quiz. Yeah, we're having a quiz either on Thursday or Friday on titrations and buffers. Okay, hands up for Thursday. 1, 2, 3, For hands up for Friday. Okay, Friday it is. Just study as though it were for Thursday, and then you'll be ready for Friday. Do you know what I mean? Like, honestly, if you understand it, you're not going to forget it overnight, right? It's not going to happen.
Are we doing the test before?
Yes. I'm thinking it would be nice to have it on Tuesday. Test Tuesday.
Yeah.
What about Wednesday? My only issue with that is that you will put off all of the electrochem stuff until after Wednesday, right? Because you will. And then we won't really have a chance to dig into electrochem before, because Thursday is a half day.
Realistically, I'm thinking like if winter break is in a day, right? Like I don't think we'll really get that far into anything.
You know our stats test is on Wednesday.
Yeah, so I'm okay with that.
Okay. Maybe you're just.
I'm going to stick with Tuesday. I think it's better for you. I think we'll be able to get deep enough into the electrochem that you can do some useful stuff over the break, or at least study, you know, do some of the questions that involve both electrochem and some other things. So like some AP questions that have a electrochem aspect that we haven't been able to do yet. Like part A is electrochem and then part B is whatever. To that end, if anybody wants the review package for Unit 2, or sorry, Acid Base 2, Acid Base 2 review is available, should you want it. Did you guys want it today? Sure, I'll put it up here. Key. Uh-oh. Is this the right one? Let me just make sure I've got it correct here.
Wait, you're right?
What on earth is going on here? Oh, I think it's okay still. It's just not formatted very nicely.
Can we take these?
Yeah, we're good. Okay, there we go. I'll just need to format it better for next time, but it works, sort of.
Wait, what do I write?
Like on this page. More. Because like I can see the concentrate, the molar, it's like 2x higher, right? So it would require less.
So you would say I have 50 mils times 0.1. I mean, maybe this would come in multiple choice and you'd just be good doing that, right? But 0.1 molar HCl or moles per liter times 1 NaOH per 1 HCl times 1 liter per 0.200 molar NaOH. And if you keep your milli here, that milli will carry through all the way through.
Oh, okay, thank you.
Yeah?
You got, hey, how they don't